Okay, all right, well, terrific. Well, thank you. This is fun already. I like the idea. And when I was asked to come talk, I thought about, well, what could I talk about that might be interesting? And so I came up with this title, Diet and Exercise, a Prescription for Our Planet's Climate Woes. Okay, so you might be wondering, why would I come up with a title like this? So I travel around the country and talk, around the world really, and talk to people about solving the climate problem. And the big thing we need to do is fix our energy system if we're going to solve the climate problem. And what I always get is, well, what will the solution be? What's the one thing that will make the big difference? Is it wind? Is it nuclear? Is it this or it's that? And the reality is there's no single solution. So I've been trying to think about, how do you explain solving a really complicated problem in a way that people can kind of relate to something in their own life, okay? So we all know, like at least me, knew that sometimes I'm overweight. And what do you do when you're overweight? Well, you know that if you do both diet and exercise, you have a much higher probability of solving your problem. And not only that if if you do exercise, you probably want to lift some weights, you want to do some walking, some cycling, some running, some swimming, because if you get a diversity of exercises, that you'll do better. And similarly with your diet, we need a diversity of things. So that's the idea behind this talk. This is an experiment. After I'm done, I would love to hear whether you think this is a helpful way of trying to describe something that's very complicated, so people can start to realize that solving this will take a lot of different actions and gain support. Okay, so that's what we'll talk about. So the first thing I'd like to start off with is, by 2100, we're likely to have 9 to 10 billion people on the planet. Right now we have about 7.4 billion people. Of the people on the planet, about 30% of them lack access to modern energy services. They don't have electricity, they cook with wood, or they cook with dung, they burn that inside their house. So basically they have very poor energy, and if economies are going to thrive, they need energy. Because if you look historically at the rate of growth of GDP, and you correlate that with growth of energy use, you find they're strongly correlated. So energy is really important to them. So the bottom line is we're likely to need more energy. So often one of the challenges we face is, in the developed world, people think about the energy situation and say, well, we just have to use less. But the reality is that we're going to need more, because there are so many people who don't have enough. So I like to think about it, we're going to need about twice as much energy. If we sort of do what we're doing today, if we use energy the way we do, if we get it from the resources that we do, we're going to need about 2 times more. Now you can say, well, how did you come up with this number 2? What's the fancy model and so forth? Well, there's no fancy model. All this says is that if everybody lives like an Italian, okay, with the energy intensity and the wealth of an Italian, that's a pretty good quality of life. And we provided this to all 9 to 10 billion people, that we're going to need about 2 times more energy. So you might wonder, well, how does what we use in the United States compared to what an Italian uses? Well, they use about 1/3 of much energy per person. So they use way, way less than we do. So this is not assuming that if everyone lived like an American, it would be 6 times more energy. Okay, so that's the challenge. And the question really is where can we get all this energy from? How can we avoid damaging the planetary ecosystems we rely on to make our planet a hospitable place? Healthy ecosystems, clean water, clean air, and very importantly, a stable climate. So this is the problem that I work on every day, and that many hundreds of scientists and policymakers and economists at Stanford work on. So just briefly, what's the problem? When we use energy the way that we do, we take fossil fuels from out of the ground, coal, gas, oil, we burn it, we put carbon dioxide into the atmosphere. And this is a graph showing from the beginning of the Industrial Revolution the amount of carbon dioxide that we're pumping into the atmosphere because of burning fossil fuels. And you can see it's gone up sort of relentless, really exponential growth in the amount of carbon dioxide we put into the atmosphere every year. And now we put around 35,000 million tons of carbon dioxide into the air. That's really a lot. Okay, so what happens? Well, when we put carbon dioxide in the air, it doesn't mysteriously disappear. It doesn't rain out of the atmosphere like, traditional pollution does. In fact, about half of all the carbon dioxide we put in the atmosphere stays there. The other part goes into the oceans, or it's taken up by plants and so forth. And so the consequence of putting all this carbon dioxide in year after year is that the CO2 concentration, or carbon dioxide concentration, has relentlessly increased, and now we are over 400 parts per million of carbon dioxide in the atmosphere. So we've dramatically changed the composition of the atmosphere. So what does this do? Well, basically, this traps heat. So the Earth is radiating heat or energy into space, and some of that is not able to escape because it's trapped in the atmosphere by this carbon dioxide. So that's the fundamental problem. So you can say, well, then what are the consequences of this? Well, there's climate change, drought, floods, extreme weather, extreme heat, habitat loss, food insecurity, wildfires, bark beetles, on and on. But it's not just about climate change, it's also about sea level rise. There are now projections that if you look at cities like Shanghai, major worldwide cities, that by another several decades, if we continue to do exactly what we're going to do, that about half of the city will be underwater. And if we continue to do that out to the end of the century, basically Shanghai ends up being a small hill surrounded by water. So sea level rise is very significant. East Palo Alto is a nearby example of something that's at risk. And it's not just that, it's also ocean acidification. When we put carbon dioxide into the atmosphere, about a third of it goes into the oceans. The ocean becomes acidic, and when you have an acidic ocean, things like coral reefs are no longer healthy. The fundamental organisms at the base of the food chain, they can no longer grow shells and so forth. So it's really a whole host of issues. So the bottom line is, this is something we should care about. If we're overweight, so to speak, this is our doctor telling us we need to get on with solving this problem. So one of the things that's been discovered, with many things, that a cause and effect are very difficult to establish, and the climate system is extremely complicated. And the IPCC, which represents thousands of scientists from around the world working now for many decades, about 2 decades, to try to understand this. And this last report, they come up with a very important observation. That basically, if you look at the cumulative amount of carbon dioxide we put into the atmosphere versus the temperature change that we will experience relative to a baseline of the pre-industrial time, that there's pretty much of a linear relationship. Okay, it's not terribly complicated anymore. And yes, there's some uncertainty, but basically there's a very linear relationship. So if, for example, we decided that we needed to limit warming to 2 degrees C, which is the globally accepted target now, that what we would find is that the maximum amount of carbon dioxide we could ever put into the atmosphere is about 3,600 billion tons of carbon dioxide. Okay, so that's the maximum. So now we know exactly how much more we can put in before we are built in to have a 2 degrees C warming. Okay, well, where are we now? Right now we're here. Okay, so you can see that we're about halfway there. And so if we keep doing what we're doing today, in about 30 years, we will have used up our entire budget of carbon dioxide that we can emit into the atmosphere. So you can see that this is a very urgent situation. It's not something that we can have the next century to solve. In fact, we need to get on this right away. And every year we delay, we use up a little more of this atmospheric reservoir. And the other question is, as well, is 2 degrees C really the right number? in Paris over this last week, there's a new movement saying, well, no, that's not good. We really should be striving for 1.5 degrees. So, but now we sort of have our marching orders set out for us. Okay, so I'm an engineer, so we like formulas and equations and all of that. And so now that we know the maximum amount we can put in, we can start having quantitative targets about how we have to change the energy system and the associated carbon emissions. So this is a very simple little equation. And it basically says that if you look at how much carbon dioxide we put into the atmosphere for every dollar of GDP. Okay, so whenever our economy, we're always using, our industry, our residences, the more money, the more wealth there is, the more CO2 we're emitting. So if we could change this factor at a decreasing rate of 5.5% per year. Okay, so every year we would need to decrease the amount of carbon dioxide per every dollar of GDP by 5.5% a year, we would actually be able to achieve 2 degrees C. Okay, so we have a quantitative target here. Okay, so how hard is decreasing the carbon intensity by 5.5% per year? Well, today, the carbon dioxide per dollar of GDP is decreasing at a rate of 1.1% a year. Okay, so we're a long way from being able to achieve this. We need major changes in our energy system. We need major changes in the way we think about our energy system. And for me, thinking about the energy system, it's giant. It is so complex. It's 10% of the global GDP is actually associated with the energy industry. It's like taking a huge ocean liner and turning it around. So when I see, oh my gosh, we're at 1.1 and we have to go to minus 5.5% per year, that makes me worried. So again, we like equations. So let's do a tiny bit of math here. Okay, so let's take our equation for the amount of CO2 per dollar of GDP and divide it into two terms, okay? One term is going to be the amount of energy we use for every dollar of GDP. And the second term is going to be the carbon dioxide emitted per unit of energy that we use. Okay, so now what we know, based on this, is that the product of these two things, energy per dollar times CO2 per unit energy, has to be equal to minus 5.5% a year. And the name for these things is the energy intensity is the energy per dollar. So that's what we'll call energy intensity. And I think of that as the diet. So basically, if we could simply reduce the amount of energy we use per GDP, it's kind of like eating less, that would help us. And similarly, if we could reduce the carbon intensity, that's how much carbon we emit per every unit of energy we use, that will help. And I think of that sort of as exercise. So here's our diet and exercise, okay? So now we have two knobs, we have two things we can change about the energy system. So when I look at this minus 5.5% a year, it doesn't look so difficult. Maybe we can double the rate of improvement of the energy efficiency every year, and we can say increase the carbon intensity improving rate by like maybe 2 or 3 times. Okay, so all of a sudden, by breaking it up in 2 pieces, having more options to help solve the problem, it makes it easier. Okay, so now just really briefly, what is the toolkit? What are the technology options that we have available? So right now, you can produce power with wind turbines, photovoltaics, at the same or a lower price than fossil fuels. So this is tremendously exciting. We couldn't have said this even 5 years ago. The other thing we have is natural gas. So natural gas is a cleaner fossil fuel than coal. It's certainly still a fossil fuel and emits carbon dioxide, but it only emits about half as much carbon dioxide per unit of energy that we use. So you'll notice that these are all color-coded. Okay, so this is red, so this means if we do this, we're reducing the carbon intensity. So it doesn't make the energy system more efficient, it just reduces the carbon output. Similarly with photovoltaics. And natural gas has two benefits. It actually improves the energy efficiency because using natural gas is more efficient than it is to use coal. And because of the lower emissions, it actually helps with the carbon intensity as well. Okay, that's what we can do today, for sure. Okay, what about things that are coming soon? Well, one of the big jobs we have to do is we need to modernize our electric grid. Our electric grid was built to have large generators and a very complex transmission and distribution system that would bring electricity to everybody. But it's not very easy to use that grid for a modern energy system that includes lots of renewables. So the technology to do this, the integration between information technology and energy technology is coming soon. We can also switch to electric cars. You know, we're lucky we live in the home of the Tesla car, but there are many other electric cars coming along. And within 5 to 10 years, these are likely to be just as cost effective as internal combustion vehicles. So that's very exciting. And then finally, energy storage, batteries, hydrogen, as ways to be able to store renewable energy when it's being generated and use it later, for example, during night when we need it. So these are coming soon, and again, we can see our color codes of efficiency and reducing carbon intensity. And then we have things that are on the horizon. So these might be available, let's say 10 to 20 year time frame. We have things like carbon dioxide capture and storage. If people are using fossil fuels in the future, it would be possible to capture that carbon dioxide and store it so that it couldn't be released into the atmosphere. We're actually learning how to make fuels from carbon dioxide and water and renewable energy. So these are called abiotic renewable fuels. They're not biofuels. They're fuels actually made by chemical processes that convert renewable energy into fuels that we could use for transportation or for firming the electric grid. And then we have some really wild ideas where you could actually take advantage of the fact that the space is really cold, about minus or about 3 degrees Kelvin. We can get our fact checker here for the temperature of outer space. So that's very cold. The Earth is relatively warm. We radiate energy out to space so we can make things cold. And we can actually use that for cooling, air conditioning, and also we found a way to, at nighttime, generate lighting with renewable energy from this source. So this is the good news. There's lots of things. So now what I just want to quickly do is just sort of go through a plan, again, the diet and exercise plan, where we combine all of these technologies. Any one of them doesn't have to solve the whole problem, but together they're very, very powerful. So to think about how this works, we can imagine that we have the 2100 baseline carbon dioxide emissions, which would be about twice what the emissions are today. And then we can start looking at ways of reducing these carbon dioxide emissions through this variety of measures. And anything that is green is we're reducing energy intensity, so this is our energy diet. And the red is reducing carbon intensity, so this is our exercise. And if it is red and green, it actually does both of them for us. So the first thing is in the developed world, we can simply conserve energy. We are really wasteful, particularly in the United States, of how much energy we use. Much of it is unnecessary. The second thing is there's a whole host of energy efficiency technologies that are available today. We can use LED lighting. We can choose to drive more efficient cars. We can have better heating and ventilation systems and so forth in our buildings. So there's a lot that we can do to reduce our energy use and consequently our emissions through these efficiency technologies. So these two together could probably reduce our 2100 emissions by about 30%. So what's next? Next we can switch to renewable energy. We can close down coal plants and build wind turbines and photovoltaic factories and so forth. So here is our first steps of the reducing the carbon intensity. Okay, the next one I'm going to put up, this one is more controversial. You're going to go, why are we doing this? So, but we, in the United States, about 35% of our electricity is produced from coal. Coal has very high emissions of carbon dioxide. It's also got emissions of a lot of other things like mercury and particulates and so forth. So we can switch to natural gas. So going back to the analogy of diet, so if your doctor told you that you needed to jog for 2 miles every day, and you said, well, gosh, you know, I'm really not ready to jog, but I want to walk for 2 miles a day. Is that good enough? And you say, well, that's not really good enough, but it's way better than doing nothing. So that's what the category of the switching from coal to natural gas represents. Next, we can switch to electric vehicles. Again, these are more efficient, and if we're using electricity from the grid and our grid has more renewable energy on it, it's got both higher efficiency and reduced carbon emissions. Next, where we still are burning fossil fuels, or our industry, where we're manufacturing cement or we're manufacturing steel, those processes might be very difficult to do with renewable energy. So we could use carbon dioxide capture and storage. So taken together, these measures, now we're down to, we've dropped the emissions by about 60% compared to a baseline. We can include some nuclear power. Again, this is absolutely carbon-free source of power. And then finally, there's going to be new technology, all those on the horizon things. And the goal will be to get to zero emissions before the end of the 21st century, and hopefully a good while before that. So here's sort of the diet and exercise plan, but that's really not enough. We all know that if we want to do exercise, we need to go to a gym, we need to, and so forth. So there are other critical factors towards making all this work. We need to develop the enabling infrastructure, so particularly electricity grid modernization. We need a huge infrastructure for charging electric vehicles, because to get the biggest advantage from electric vehicles, we really should be charging them during the daytime when we have large amounts of electricity from solar energy. The second thing, we need to figure out what are the best choices, and what are the best choices not in for the whole world, but in a particular place. So we need technology and energy systems assessment to help policymakers make good choices. And life cycle assessment is one of those important ones. For example, how much water does an energy technology use? If you can find a technology that uses no water to produce energy, that's highly advantageous. So life cycle assessment allows us to answer questions like that. We need to get money to invest in all of these new technologies. Everything on this list, the only thing on this list that's free is conserving more energy. And even if at the end of the day it's more cost effective, it still does take a capital investment. So getting the financing right is really important, and also getting the incentives right. If we could have a revenue neutral carbon tax, we wouldn't have to work so hard to incentivize people to do all this. And then finally, behavior and public opinion are really key, because if at the end of the day people don't choose to go along with a plan that deals with these problems, doesn't matter how good the technology is, we're not going to be able to make progress. So just to wrap up very briefly, a portfolio of solutions, diet and exercise, everybody contributes, economy-wide, and technology, finance, and policy innovation. Let's invent the future. So I just want to add one thought for those of you who were really hoping that I was going to talk about diet and exercise as a solution. Personal choices are really important, and it turns out that eating meat is very energy intensive to produce meat. So eating grains and vegetables can make a big contribution. And exercise, bicycle riding, walking, and so forth. So these are the kind of real choices that we can make so that we can contribute to the decreasing of the carbon emissions into the atmosphere. So thank you.